Hi guys, let me just admit everybody to the class here. How's it going this morning? Everybody's asleep. Shy. Oops. All right. So let me go ahead and get started talking about stuff as I'm letting more people in. Today we're going to cover chapter 2.8 that is going to be on our exam. It's a short chapter just dealing with other trig functions, tangent, cotangent, things like that. Towards the end, if we have a few minutes, I'll answer, a couple homework questions. Remember this week, what we have due is 2.6, 2.7, and 2.8. 2.8 stuff should be up online. Want to take a look at those things. I will post the solutions for 2.4 and 2.5 later today, and then I'll post 2.6, 2.7, 2.8, those solutions. I'll post them probably Wednesday late afternoon. I want you guys to have a chance to actually try it and work it through, and then come and ask questions on that. But you will be able to see those solutions before you take the exam. So we, just as a reminder, have an exam on Thursday. Our exam is for a whole class period, so it takes 60. It's scheduled. It's designed to take 65 minutes. Plus, our department is giving us 15 minutes to hang on a sec. 15 minutes to take a picture and upload that to our Canvas page. The exam is a timed exam, so what that means is you have to finish it within the time frame and make sure that you upload it within the time frame. Otherwise, the Canvas window will shut and you won't be able to upload it. So keep that in mind. That means that you may not, or you should not start it any later than say 10:30 on Friday morning. Okay, this thing is going to go, it'll become available at noon on Thursday until noon on Friday. Okay, so keep that in mind. Now I wanted to ask you guys a question. We voted on this in my 8 o'clock Calc 1 class. So the exam, right, is going to be basically 80 minutes starting on any time within a 24-hour window starting on Thursday. Now, the question for you is, do you want to have a class on Thursday? Okay. Mostly, let me tell you what I've done with my other classes when we've had these exams. I'm taking time from your other classes, right? So that you'll have 80 minutes that you'll need to allocate to take this exam. It doesn't seem fair to take double dip it, to take time for a class and to take time for an exam. The department usually lets us not have a class when we have an exam so that you guys have time to do work for other classes. So you guys can think about that. My other class, my 8 o'clock class, voted not to have a class period on Thursday. Okay, because we have the exam that starts on Thursday. So if you guys want to tell me, in the chat, you can tell me, offline, or you can say it out loud if you want to have a class on Thursday. Yes or no? I'll still have office hours on Thursday, although I ask that you not come to office hours to ask me technical questions if you've already started the exam. Okay, it doesn't seem fair. You can email me things like, there's a typo in question 1 or something like that. That's different. But how do I answer this type of a problem? I can't really answer that, especially if you've started the exam. Okay, so Wednesday we'll have a review. Thursday class, yes or no? So far we have no votes. Most people have chosen not to have class on Thursday, which I think is actually fair, not to have class period scheduled on Thursday because you have an exam. And I don't want to take class time away from your other classes too. Okay. Okay. So far so good. Okay, you guys can think about it and then let me know too. All right. Okay. So it looks like we're voting not to have class on Thursday, which I think is actually fair since you guys you want to allocate that time for your exam. Okay, Let me read this question. So the exam is just like the quizzes. You download a PDF, then resubmit it after an hour. Yeah, so that's how I'm going to set it up. So the exam will be set up like this. Except that the quizzes I haven't set a timer on, even though it's been an honor system that you've needed to upload them. The quizzes were a half hour. It's been an honor system for you to upload them within a half hour. The exam is a timer, and I believe that if you max out your timer window, then you can't upload it. So what happens is when you'll start the exam, right, you make sure that when you start it, you get one shot to take it, okay? When you start the exam, the timer starts. Okay, so you have like basically 80 minutes to do it. And that 80 minutes includes taking a picture and uploading it, okay? PDF or JPEG format. Now, when you do this, you're gonna basically, hang on a second. The first question on the exam will be a PDF, which is the exam. Okay, so you're gonna download the exam as a PDF. You can either print it out and take it on the exam page, or you can just look at it on your screen and then write down your answers on a separate piece of paper and then take a picture from that. So you don't need a printer in order to do the exam. But you do have to upload your answers, the PDF or JPEG of your answers into the Canvas page. If you try to upload it after the time window, after the 80 minutes, then I don't think Canvas is going to let you do that. Okay, so make sure that you're aware of that time period. Technically speaking, the exam is open book, open notes, although please don't be lulled into a false sense of security about that. How open book, open notes exam works, how they work is like you pretend like you're taking a class in class, taking an exam in class, okay? You prepare, you study, you do everything as though you were to come into class and take it without any notes, okay? Your calculators are allowed. When you come in, when you take the exam at home, right? The notes, open notes means basically like, oh, I can't quite remember what's that formula or what's that derivative. You can just quick look it up and then you have it, okay? So in that sense, it's different, but please, if you think I'm just gonna be able to kind of look up my notes as I'm taking the exam and do it, you will run out of time, okay? So the open notes, open book exams can lull you into a false sense of security and you can end up doing worse because you think I've got plenty of time to look things up and you just won't. Okay, so prepare and study for it as though you were taking an in-class exam. Does it just save the time you initially downloaded it? Does it just save the time? I don't think I understand it, but I think it includes the time that you download it. So that 80 minutes is when you open up the exam. Does the timer start when you download? I believe the timer starts when you hit start, and then it brings up the first question. The first question is a PDF. You click on that PDF and there it is. And that whole process should take you about 5 seconds to open it up, click on the PDF, and then the PDF is opened up on your screen. So whether you want to print it out or just look at it on your screen is up to you. Okay, but yes, the timer starts, it's a separate timer window. So when you load it up on Canvas, you're going to go into, it's going to say, okay, you ready to take the exam? Are you sure? Yes. Are you sure? You're going to hit start. And then it's going to bring up question one. Question one is the PDF that you download. Okay, and that question one is the whole exam. I know these online exams are a little cumbersome, but that's like our best way of setting it up. Okay, so the timer starts when you hit the button, essentially to start, and then you download it from there. Okay. Anyway, all right. So before we get started, so I was grading. Excuse me. I was grading the quizzes, the 2 most recent quizzes, and I put the solutions up online. I'm going to start putting up the older quizzes solutions up online later today. So you'll see those. I'm putting them up in the modules page. So where it says, here's the quiz, in the modules page, I'm putting the solutions right below that so you can see it. I wanted to talk to you about a couple of things on the, I wanted to go over a couple of questions. So this is the quiz on chapter 2.4 and 2.5. This is the one that we just took. Question number 4. Okay, so I saw most of you guys, like 95% of you guys, got this problem, you worked it through, you basically did a really good job, but I wanted to address a couple of things that I saw on here. So this one said, use logarithmic differentiation to find the derivative of this function y equals. So we'll write that down in a minute. So if you are told, as you will be on the midterm, as you will be on the final exam, logarithmic differentiation always comes up on the final exam, which means it'll be on the midterm as well. If you are told to use logarithmic differentiation, you must use logarithmic differentiation. So if you use the quotient rule, which technically will also get you the answer, but if you use the quotient rule, you get no credit. And that's a bummer because you're going through and you're doing this stuff, but you didn't answer the question. So this question is designed to test your ability to do this particular skill, right? The skill is logarithmic differentiation. We need to know this skill because we're going to need it in future classes to solve and answer much more complex questions. And we want to be able to use this because the quotient rule is going to be too cumbersome, and the logarithmic differentiation is going to actually get us there. It'll be the only way sometimes to solve a problem. So so if you use the quotient rule, you don't get any credit. I think I gave 1 point, just for trying, but on the final exam, you'll get no credit. Okay, so just keep that in mind. You must answer the question that's being asked. So please be sure that you're reading things right. Also, let's just be sure this one is going to exploit our properties of logs pretty heavily. Remember, there were 3 properties of logs that we talked about. The first one was the multiplication, addition property, which basically said I'll use the natural log a over b. Oh, I did the quotient rule, sorry. Natural log of a times b. So a times b, this will be true for a log of any base. This is log base e, but natural log of a times b is natural log of a plus natural log of b. Okay, so multiplication addition, right? I've got a product of 2 terms. Now this does not apply when I have natural log of a plus b inside of a bracket. That's just what it is, okay, a times b. Second rule is our division, subtraction. And this one is natural log of a divided by b, and this is natural log of a minus natural log of b. This one, like the problem in our quiz, gets complicated when I have multiple terms in my denominator, and I have to keep track of this negative sign here. Our last property is our exponent. So this is a natural log of, let's write it like this. It could be x squared or natural log of 2 raised to the x. This is the one that we really like our logarithmic differentiation for because it gets our variable out of our exponent. But let's do them both. So this is 2 ln of x. This is x ln of 2. One of the things that I saw, so ln of 2, this is just a constant term. That's a number. I plugged it into my calculator, I'm going to get some number, right? This right here, I can, it's a coefficient. Even though we're writing it x times that, it's really ln of 2 times x, right? In terms of how we write our coefficients. So if I were to, let's say if I've got x ln of 2, and I want to take the derivative with respect to x, sorry, d dx. This means I'm taking the derivative with respect to x. X is the variable. So I'm just doing the power rule here, right? This is my coefficient, it's equal to some number. Okay, we leave things in terms of ln when we got it like that. So if I were to take this derivative, my power rule says, well, I'm just going to do ln of 2 times x to the 0, which is this one. So ln of 2, that's it, right? You're not going to do, I'm not going to take the derivative 1 over 2 times the derivative of 0. I mean, it doesn't make sense. Okay, this is just a coefficient. Be careful. We're exploiting these properties of logs, okay, in this particular problem, and that's how we're going to be solving the logarithmic differentiation. With all that preamble, let's go ahead and take a look at question number 4. So question number 4 says we have to use logarithmic differentiation 2 to the x times 1 plus x all over x squared times x plus 2. Okay, so this is our function right here. So I need to do in order to find y prime, I need to use log differentiation. We have to. We can't use quotient rule. We're told to use logarithmic. So the first thing I'm going to do is I'm going to take the natural log of both sides. And I could take the log base 10, the log base 3, whatever, but we are working in natural logs, right? So we're working e to the x is a function that we use a lot in these classes. So we tend to focus on the log base e, which is our natural log. So I'm going to do that. So I'm going to go the natural log. So I'll break it up into 2 pieces. So 2 to the x times 1 plus x minus x squared times x plus 2. Now I saw some of you guys try to distribute 2 to the x into these terms here, and then x squared. Then you're just making life more complicated for yourself because now you've got to think about product rule and stuff like that. Just leave it like this, because also you may be dealing with, you know, questions where I've got an exponent here and an exponent there, like 1 plus x to the 5th, x plus 2 to the 10th. I'm not going to try to, you know, expand that and then combine things. So leave it like this. Our properties of logs, I have product of these two terms, a product of these two terms. So further exploiting our properties of logs, we're looking at the ln of 2 to the x plus ln of 1 plus x minus, I'm going to do this, ln of x squared plus ln of x plus 2. Okay, now I put a bracket here just to remind myself, because I've got to distribute that negative to both of these terms. This becomes, oh, ln of 2 to the x plus ln 1 plus x minus ln of x squared minus ln of x plus 2. We like to put these, you know, multi-term questions on the final exam to see if you remember these properties of logs that you have to distribute. It's a common mistake on the final exam. You're going really fast, you know, you're doing all these problems, you've got a lot of things to think about, and then you forget to distribute the negative, and it's going to throw off your answer. All right, so let's deal with our exponents. So I'm going to do my exponent loss. I've got x ln of 2 plus ln 1 plus x minus 2 ln of x minus ln x plus 2, and this is equal to the natural log of y. So now all I've done is just set things up. So I take the derivative of both sides, which means I'm going to do 1 over y times my chain rule dy dx. Remember, this is the thing that I'm solving for. You have to do the chain rule on this side here because I have to solve for that. So now I'm doing this with respect to x. So here, like we said before, this is just a coefficient. So when I take the derivative with respect to x, this is just natural log of 2. So here, this is my u. So I go 1 over that, and I would take the derivative of what's inside, which is just equal to 1. Keep that in mind. I mean, right now, we don't have to worry about it because it's, you know, the derivative here is just equal to 1. But so now I have 2 as a coefficient. The derivative here is 1 over x times the derivative of what's inside, which is just equal to 1, minus 1 over x plus 2 times my chain rule, my derivative is equal to 1. Okay, so here's where I'm at. I want to get things, I want to get rid of the y. I just want to solve for dy dx. So I have to multiply both sides by y. Right, so it's going to give me, I'm going to put it up front, y times ln of 2 plus 1 over 1 plus x minus 2 plus x plus 2, like that. Okay, so don't worry about finding common denominators, just leave it. You know, this is how we're doing it. Now I have to substitute in my original function, which is what we were given at the beginning, because I want things in terms of x. I don't want to have a couple variables there. So I'm going to substitute that back in for y. So my dy dx equals my original function, 2 to the x, 1 plus x all over x squared, x plus 2 times, right, our derivative ln of 2. Okay, and then that's it. Don't multiply things out. Don't combine, like, you know, don't worry about finding common denominators or whatever. This is it. Okay. But the biggest thing that I found was some of you guys got confused on the properties of logs. How do I break things apart? You know, if I distribute all these terms, is it going to make it easier? It's not. Just leave it like that, because look at how nicely everything just broke apart. Right. Also, some of you guys forgot this ln of 2 is just a number, and you tried to get fancy with the derivative or product rule on this here. You should end up at the same spot anyway, but you're giving yourself more work in the end. More work means more likelihood of making a little trivial mistake that you'll lose points on. Okay, so logarithmic differentiation. You have to, if you're told to use that method, you have to use that method. Just like on an exam, if you're told to use the quotient rule, you have to use the quotient rule. If you're just told, hey, have at it, find the derivative, you can use whatever method you want. Quotient rule, logarithmic differentiation, whatever, okay? But if you're told specifically to use a method, make sure you do that. You have to answer that question. If you left the last 2 terms in brackets instead of distributing the negative, would be wrong. Nope, not at all. So you would say minus and then this plus that. It's the same thing, totally the same thing. Nope. And if I I don't think I wouldn't have marked off points for that. That would have been totally fine. But you definitely need the brackets because it's both of those are negative. They happen to be in your denominator. Okay. Leaving them in brackets isn't going to affect your derivative anyway, because now we have this piece plus this piece plus this piece. Remember our theory of linearity, right? Says when I go to take the derivative of things that are adding and subtracting together, I'm just taking the derivatives of those individual pieces and then adding and subtracting those. Okay. So we're good with that. The next question was looking at the quiz for 2.1, 2.2, 2.3. Chapter 2.1 to 2.3. I think I posted solutions for these already, but I wanted to make sure that we talked about it because I saw some kind of recurring themes on the errors here. So this one was also question 4. This is the inverse derivative function. So we're given the function f of x equals x squared plus 2 over x. And then we're asked to find the derivative of the inverse of this function at a particular point. Okay. Now, most of you guys got the right idea and you remembered that formula that we have. So if I say my inverse function at a particular value, I'm taking that derivative is equal to 1 over the derivative of that function evaluated at my inverse. Okay. Okay, we call this g of x, right? So this is g of x at b, taking that derivative. I'm taking f prime of that value here. Now, most of you guys got this point. You remember going back when we did this in class, we do a nice graph. We do a graph of the function. We do a graph of the inverse. We talked about the derivative at a particular point, right, an xy point. We drew that tangent line and we found the point, the corresponding point on our inverse, how we switched the x and the y, so then to find the derivative of our inverse at that particular point, we needed to find the corresponding point on our function and then exploit the relationship of the derivatives and the relationship of the inverse functions together. Some of you guys tried to find the inverse by switching the x and the y and solving for y. You really can't do it with these functions, okay? And then and maybe you can find a way to find this inverse, but we may give you a function that's even more complicated and you can't, switch the x and the y and work it through. So you must be able to think about how I can relate the function and the inverse. Okay, so we were given some other pieces. So we're told to focus on the interval 1 to infinity. And this is important because when I graph the function, I get multiple solutions, right? This is an equal sign here. I'm running out of space. So this tells us I'm only focusing on one of those solutions, right? Otherwise, I would basically find, if I didn't, limit my interval, I said, it's minus infinity to positive infinity. I have 3 different possibilities. I'd have to find the inverse in the tangent lines at all 3 of those. But we were limited. We limited our interval, and we're told to look at b equals 5. So let's think about what all of this means, okay? Just to spell this out, because this is important. So I've got my function here. Okay, so this right here, so this b equals 5 is on the domain of the inverse function, which means it is on the range of our regular function, our non-inverse function. So if that's on the range, then I can say f of x equals 5, which is equal to x squared plus 2 over x. So what I did was I want to find, where this is true. So I subtracted 5 from both sides and I got 0 equals x squared plus 2 over x minus 5. Okay. And then I plugged it into my graphing calculator. And I got a graph and I could see that there were 3 solutions. I didn't graph it, I didn't bother, but there are 3 solutions to this where this function right here crossed the x-axis. There were 3 different values, x equals this, x equals this, x equals this. Now, given the interval that they told me, from 1, not inclusive, 1 to infinity, there was only one solution, one x value, but only one solution in the interval. And that solution that I got, and I used my graphing calculator to find out what that solution find out all those solutions, I said, what are the zeros of this function? Okay, so you are totally fine with saying by graphing calculator, x equals, this value, this value, this value. Only one of these solutions is in the interval, and that was x equals 2. That's a 2. Okay, so what that means is this. Okay, let's write it down. So if I say f of 2 equals 5, okay, because I found this, now the relationship between the function and its inverse means that f minus 1 of 5 equals 2. Okay, so without even ever knowing what my inverse function is, I'm finding points along that graph. I can keep doing this forever. I can actually graph out my inverse function by finding points along my regular function, right? So I find these corresponding points, and then I can, solve it from there. But we're just asked at this particular value here, so I'm not going to go hog wild and do other points. So all I need to do is look at when the inverse is equal, and I have x equals 5. On my inverse, I get my function's equal to 2. So I can exploit this, right? So remember this formula here. I need my derivative of my regular function. So my regular function derivative, I'm going to use the power rule. So that gives me 2x, right? The power rule, this is 2 times x to the minus 1. So the power rule says minus 2 all over x squared. Okay, so now my formula says I take my inverse, right? My derivative, and I plug it in. So f inverse of 5 is equal to 2. So this is f prime evaluated at 2. So I'm going to plug in 2 into my derivative. 2 times 2 minus 2 times 2 squared, which is equal to 4 minus 2 over 4, 4 minus 1/2, which is 3.5, which I'm going to write 7 over 2. So some of you guys got to this point, you forgot to do 1 over that value. So f minus 1 of 5 derivative is equal to 1 over 7 over 2, which is equal to 2 over 7. Okay. Some of you guys wrote 1 over 3.5. It's technically correct. I didn't pick up points for it. It's just not a way that we write numbers. We don't usually combine fractions and decimals. You should, if you're going to write 1 over 3.5, give it to me just straight as a decimal. Okay, or convert it to a fraction and then just give it to me straight as a fraction. Try not to mix your metaphors. Okay, so that's your answer here. But remember, if you can't remember, like, why am I doing all this stuff here? It seems really cumbersome, right? Remember the graph that we did, and it should be in our lecture video. I forget. This is probably chapter 2.3. Take a look. For the graph that we did, we talked about here's our function, here's our inverse. How do we get, exploiting the derivative of our function at a particular value? How do I get the derivative of my inverse at that corresponding value? Switch the x and the y. So without knowing even what my inverse function is, I can even build up my inverse function based on all these different derivatives. Okay. So these were 2 that I saw, people kind of struggled on, but I wanted to talk about them in person because wanted to make sure that we were on the same page about that. Okay. I guess all set. I think most of you, did these just fine, but just make sure that you're clear on this, because these things, you'll definitely see this on the midterm exam. It's, these things pop up. This one for sure, the logarithmic differentiation is always on the final. The inverse derivative, it's usually like a 70% chance it'll be on the final. You'll probably see it. So you want to make sure that you don't lose those points on the final exam in particular, because it's worth a lot there. Okay. All right. So with that said, let's go ahead and talk about chapter 2.8. You guys should have the lecture examples. They're up online, and our homework for 2.8 should be posted up online as well. The homework for 2.8 is due on Thursday, so you can ask me questions about it in the office hours or class on Wednesday. All right, so chapter 2.8. So these are other trig functions. Okay, so the other trig functions we're going to talk about are tangent, cotangent, secant, cosecant. Okay, we talked last time about sine and cosine, right? The fundamental trig functions. These other trig functions are made up of combinations of sines and cosines. Okay, so hopefully the first part of this discussion until we get to derivatives, hopefully it's a review, but let's just go ahead and be on the same page. So when I talk about my tangent function, and x is equal to sine of x over cosine of x. I have a function in the denominator, which means I've got places where this might be, my denominator might be equal to 0. So I have to find those values and discard them from my domain. So x can't be equal to, let's see, cosine is equal to 0 at multiples of pi over 2 plus k times pi. Make sure you have the multiples on there, right? Our cosine functions, they go on forever. Okay, they repeat forever and ever. Our tangent functions, likewise, are going to repeat forever and ever. Okay, so we've got to be able to include multiples of pi over 2. Now, k is an integer, positive and negative integer, okay, including 0. All right, so cotangent of x, cosine of x, sine of x. Again, I've got a function in the denominator. I have a chance for where is my sine equal to 0? My sine's equal to 0, right, at multiples of pi, including 0. So it can't be equal to k times pi. Okay. So I'm looking at my denominator as a place for exclusion. Cotangent. Okay, and then my secant, we'll do secant first. Our secant function, okay, we write it SEC, secant of x, and secant function is 1 over our cosine of x. So again, right, so where was our cosine equal to 0? I have to exclude those values, pi over 2 plus k times pi, because it repeats again and again. And then the cosecant function, CSC, cosecant of x, this is 1 over sine. So again, I'm looking, can't be equal to k times pi. Their exclusion values. Pythagorean identity, we talked about that last time. Right, so this was based on our unit circle and the Pythagorean theorem. Cosine squared of x plus sine squared of x equals 1. Okay, a squared plus b squared equals c squared. That's our Pythagorean identity. Now, if I divide both sides by sine squared, sine squared, sine squared, sine squared, or if I divide both sides by cosine squared, I'm going to get 2 more Pythagorean identities, but they come from this right here. And 1 plus tangent squared of x equals secant squared of x. This is if I divide everything by cosine squared. And then the same thing, 1 plus cotangent squared of x equals secant squared of x. Okay, so 2 more Pythagorean identities. Make sure you just memorize this one. You can get these 2 by dividing either by cosine squared or by sine squared. Okay. All right, let's take a look at some of the graphs, because we're going to need to remember what these graphs look like so that when we draw asymptotes or exclusion areas, we'll know my graphs. Y equals tangent of x. All right, so I've got my x-axis, my y-axis. So my tangent function, sine over cosine, I have to exclude pi over 2, multiples of pi over 2. So first thing, I'll draw in pi over 2, also inclusive minus pi over 2. Okay, which means, right, tangent is equal to 0 over 0. Okay, because at 0, my cosine is equal to 1, sine is equal to 0. Okay, I'm going to draw out pi over 4 minus pi over 4. Pi over 4, right, these are values where our sine and cosine are equal to each other, so a tangent is equal to 1 or minus 1. That gives me kind of a rough draft for what my tangent function is going to look like. Then this thing's going to repeat again and again and again. Okay, so tangent function is an increasing function, right? And it's periodic, has a period equal to pi. We'll do the same thing for cotangent and take a look. All right, so we said this was cosine over sine. We can't do multiples of pi, but that also includes 0, right? Because sine is 0 at 0. So I got to put an asymptote here. I'm going to do it just slightly off so you can see that it's there. And then I have another asymptote here. This is at pi. Another asymptote here. This is at minus pi. We can have 1 minus 1. I've got pi over 4. So here's pi over 2. Pi over 4. So it's going to look like this. this. So my cotangent function goes like down like that. And then it repeats. I'm not trying this very well. There. Okay, so it repeats over and over again. Okay, it's a decreasing function. It helps especially to have these in your mind. In Calc 2, we do a lot of inverse tangent graphs. And so we want to be able to think about what does our tangent look like, so I can easily take the inverse of it and then kind of plot it out and think about what's happening at infinity or minus infinity. Okay, when we go to evaluate stuff, just to kind of keep that in the back of your mind. All right, let's graph out the other ones. So y equals secant. Okay, so secant function, our x, here's our y. So secant is 1 over cosine, right? So we again have to look at pi over 2, multiples of pi over 2. And so I'm going to start doing this. Here's pi over 2 minus pi over 2, right? And then these are multiples of pi. So then I've got, this is 3 pi over 2. Okay, so now what happens is, here's 1, here's minus 1. So now secant is 1 over cosine. You can imagine a cosine function, right? Like looking, you can imagine it like that. So what I do is I take my cosine function and I flip it. So I can even sketch out a little cosine function. Wherever it crosses the x-axis is where I put a vertical asymptote, right? What's left behind gets flipped, right? So then, and then this is down at minus 1. This is down at minus 1. I'm drawing these offline here. Okay, so this is my secant function. The graphs will help you visualize, you know, what you're trying to do. Secant of x. Okay, so I'm going to also graph this one out too, so we can visualize. Okay, so cosecant was 1 over sine, right? So I have to worry about pi and multiples of pi. So I've got an asymptote here at 0. I'm going to draw that just off so you can see it. Then here's a pi. Here's minus pi. Draw that out. So you can imagine if I had a sine, there's 1, minus 1. So if I had the sine function, it would go like this. Right, so that's where our asymptotes are coming from, right? So halfway here, this graph goes like this. Secant, cosecant are the same graph, but just phase shifted, just like sine and cosine are the same graph, but phase shifted. Right, and then down here, if you can't remember what these graphs look like, remember cosecant is 1 over sine. I'm going to draw a sine function, right? I'm going to draw a cosine function like this, and that's how I get these graphs from. Okay. All right, so hopefully that was a review. Give you guys a chance to finish writing that down. And then we'll talk about derivatives. Guess I'll set with that. Okay. All right, so let's talk about derivatives. This is actually a theorem. So these are derivatives. Okay, so derivatives of tangent, cotangent, secant, cosecant. Okay, now to get these, you'll ultimately want to have these tucked in your memory somewhere, right? But if you can't remember it, you can always do the quotient rule to find out what the derivative is. Okay, so we'll do the quotient rule on tangent just so you can see how it comes together, and then we'll talk about it for other ones. So I've got my tangent function. I want to find the derivative. I'm going to give it to you. It's secant squared of x, and then in a different color, I'll work it through. So my tangent of x is equal to sine over cosine. Okay, and if I want to find its derivative, okay, I have to do my quotient rule, which says the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, see, I just went through the quotient rule dealing with function in the numerator, function in the denominator. So let's bring it together. So cosine times cosine is cosine squared. Minus times minus makes it positive. Sine squared over cosine squared. Okay, this is our Pythagorean identity, right? So cosine squared plus sine squared is equal to 1 over cosine squared. So 1 over cosine squared, well, if 1 over cosine is equal to secant, 1 over cosine times 1 over cosine is secant times secant, which is, oops, secant squared. Okay? So that's how we get it. I'm just going to give you the derivatives for the other functions, but if you forget, you'll just go through the same thing. Now for the 1 over sine, like for our cosecant function, I would do the same thing. So like bottom times the derivative of the top. Derivative of 1 is equal to 0, right? So you can go through the same thing, but think about what's your top function. My top function is y equals 1, right? So you can work it through like that in your mind. All right, so let's go ahead and do the rest of them. Cotangent of x, their derivative, I'm going to get minus the cosecant squared of x. Okay, it's minus because of the same reason that we have here. Okay, I've got secant of x. I want that derivative. This is tangent of x times the secant of x. What happens is this comes out to be sine of x all over cosine squared of x. Right, this is squared, right? So what that means is I've got sine of x all over cosine of x times 1 over cosine of x. So sine of x over cosine is tangent, 1 over cosine is secant. So that's where these are coming from. Okay. Sorry, cosecant of x. I want to take that derivative. I'm going to get minus the cotangent of x, cosecant of x. And again, this is like, this comes out to be equal to minus the cosine of x over sine squared of x. Okay, so then we break it, we put things together. If you get an answer like this when you do your derivative from quotient rule, right, you're going to get an answer like this. Make sure that you combine it. You recognize, right, one of those cosines attaches to a sine to give me cotangent, and then I just have 1 over sine left over, which is a cosecant. And the negative comes from how we do our quotient rule here. Okay, so those are our derivatives. Give you guys a chance to finish writing that, and then we'll take a look at our lecture examples. Okay. All right, so I'm looking at my lecture examples for 2.8. Why did it make it all blurry again? That's weird. Okay. So x tangent of x, when I go to take that derivative, right? Look, I've got 2 terms. I need to do my product rule. Okay, so just because I have a trig function in there doesn't mean I can't use all of my old rules, right? So I've got a product rule I have to take into account. So my y prime says I'm going to do first times the derivative of the second, and squared of x, plus the second tangent of x times the derivative of the first. I put the 1 in so you can see I'm taking the derivative. Okay, now I'm going to put it together. It's going to be x secant squared of x plus tangent of x, and I'm done. I've combined it as much as I can. Okay, this one here, 7 times the cosecant of 3x. 3x, that's my chain rule I need to think about. You can think about that as like a u, right? So when I go to take that derivative, I have my coefficient. Okay, I have cosecant. I need to take the derivative of cosecant. Well, we said cosecant derivative was minus cotangent of x, cosecant of x. You can think about this as being like a u. So whatever value I have here, 3x, I have to repeat that in my derivative. So that's going to be minus cotangent of 3 times x times cosecant of 3 times x. Now my chain rule says take the derivative of what's inside. Okay. So now I'm going to put it all together in my y prime. I've got a minus 3 times 7, so minus 21, cotangent of 3x times cosecant of 3 times x. This 3x is a part of my cotangent or my cosecant. I can't do anything more with that, right? It's a part of this function right here. Okay, don't be tempted to, you don't use parentheses, you're gonna be tempted to multiply everything through. Okay, it's that u. Right, so if I think of my u as 3x, my du is times 3. Okay, so this is cosecant of u. When I take that derivative, it's that derivative times du. All right, secant of x, cotangent of x over x. Oh, look at that. We have a quotient rule on that term. Okay, so this is why ultimately, you want to be able to remember what these derivatives are, because if you can't remember cotangent and you want to do the quotient rule on it, do it off to the side and figure out what the derivative of cotangent is using your quotient rule, and then plug it back in because you have a quotient rule that you're doing for this whole term, cotangent of x over x. Okay. All right, so let's go ahead and do it. So my derivative of secant, we just said that right here. Okay, so my derivative of secant, I'm going to plug that in. That's tangent of x, secant of x plus. Okay, now I'm going to do the quotient rule. So it's going to be bottom times the derivative of the top minus cosecant squared of x minus the top cotangent of x times the derivative of the bottom all over the bottom squared. Okay, so now I'm going to put these together. This is going to look like y prime is equal to tangent of x, secant of x, right? I'm going to go plus, and I'm going to put each term as negative. I don't care if you want to minus cotangent of x all over x squared. You can make this minus, and then these are all positive. I don't care. However, it makes more sense to you. Okay. Okay. So remember our rules. We're still applying them, right? Even though we now have trig that we're working with. All right. Example 2. Scroll up just a little bit. Example 2 says, find the critical points of this function, w equals e to the minus theta secant of theta. Theta is my variable, right? Critical points implies I need to take the derivative, set it equal to 0, and then solve for theta. Okay. All right, so let's write it out. So w equals e to the minus theta secant of theta. I've got two functions, this one and this one, so I need to do the product rule. Okay, so my w prime is going to be the first, e to the minus theta, times the derivative of the second. This is tangent of theta, secant of theta, that's secant of theta, plus this second, secant of theta, times the derivative of the first, minus e to the theta. Okay. All right, now I need to set that equal to 0 and then solve for theta. Okay, so we're going to handle this like we do with algebra. So I have an e to the minus theta and e to the minus theta. I'm going to factor that out. I could factor out an e to the minus theta and a secant, but I'm going to keep all the trig in one spot. It's just a style. You can factor them both out. So I'm going to factor out e to the minus theta, and I'm going to get tangent of theta, secant of theta minus secant of theta. That minus comes from this multiplier right here. And I set it equal to 0. So now I have this term and this term that I need to set equal to 0, all my factors. So if I had factored out the secant here, I would have e to the minus theta times secant times tangent of theta minus 1. It's just, you're going to do the same thing, but just in different steps. All right, so set each factor equal to 0. E to the minus theta equals 0. E to the minus theta equals 0. I'm not sure. I think when I graph it out, e to the minus x, I graph it. Oh, look, it asymptotes down onto my axis here. It's an asymptote. It never is equal to 0. So this one has no solution. Okay, no worries. Let's do this part here. So I'm going to factor out a secant of theta and then a tangent of theta minus 1. And we're going to set those equal to 0. So I've got this term and this term. So this one, secant of theta equals 0. All right, secant of theta, we just did that, right? So let's take a look at our graphs. Secant of theta, I'm not sure, but I think, yeah, I'm right. Look, secant of theta, this function here is never going to be crossing the x-axis, right? It's floating above the x-axis, floating above, but floating below, which means that this has also no solution. Okay, I'm going to do this one. Tangent of theta minus 1 equals 0. Okay, now I'm going to solve for theta. tangent of theta equals 1. And now maybe possible you may have a function that never, doesn't have any critical points. So, okay, so just go through the algebra and take a look at each piece, right? Getting no solutions is possible for a function, but you just have to show why. Okay, so this one we're going to do. So tangent of theta equals 1. So I'm going to take the inverse tangent 1 to get my angle, right? So at what angle of theta is my tangent equal to 1? This is when theta equal to pi over 4 plus k times pi. I have to do the k times pi, right? Because think about this is my tangent function, right? So right here, so pi over 4, but then I have another pi over 4 right there. And I'll have another and another, and I have another pi over 4 right there. Okay, so I have to include all those repetitions of pi over 4. Okay, so unless I specify an interval, if I say this is just between 0 and pi, or 0 and pi over 2, unless I give you an interval in which to focus, you have to include the repetitions here. So that's your answer. So for this whole thing, the only critical point that we have is that pi multiples of pi over 4. Okay, so give you guys a chance to finish writing that, and then we'll do our last problem, which is a word problem. You guys good? All right. The last problem. The last problem says, we'll read it and then we'll start drawing pictures. Okay, so we've got a lighthouse that's 0.25 miles straight out from the beach. So I'm actually going to start drawing pictures as we go. So I've got this lighthouse, like that, and it's 0.25 miles straight out from some beach. Right here, this is 0.25 miles. Okay, and it hits the beach at point P. It completes a full revolution. So, I've got this, it goes full circle in 8 seconds. So that means I've got 2 pi radians equals 8 seconds. So this seconds also sets up our parameter, right? This tells us our distance is in units of miles. This revolution time period tells us our units in time, which is seconds, okay? We've got this child running along a beach, and they want to follow the beam of light. Okay, so the beam of light, right? So the lighthouse is offshore. It's going to hit the beach, kind of cruise along the beach, and then it goes out in the ocean, comes back, cruises along the beach, and they want to follow that beam. They want to run along, chase that beam of light as they go. So how fast do they need to go to keep up with that beam of light, right? So how fast must a child run to keep up with the beam when the beam is hitting the beach at 0.5 miles from 0.5 miles from P? Okay, so this is our x value here. We're going to go when x is equal to 0.5 miles. Okay, so I'm kind of drawing that out. Now this is forming an angle theta, right? So you can think about theta, going to form that full complete circuit. Theta is my angle that this beam is hitting as it's going all the way around. Okay, so start taking notes. So how fast is a speed measurement, which is our velocity, right? Our velocity is change in distance over change in time, right? Well, our distance we're measuring in terms of x, okay? So that's going to be dx dt. Delta x over delta t, right? We write it in derivative terms as dx dt. So that kind of gives us, we're starting to kind of think in terms of calculus. T is in seconds, right? And then start making notes. X is the distance in miles from P to the child. Okay, and this is a function of time. It's a function of time because the lighthouse beam is moving, right? And the child is moving with the beam. So that's why our x is a function of time. Okay, that helps us remember because we're talking about how fast, what's our speed. Okay, and then we're going to say theta. Everything that we do is in radians. Be careful, make sure that your calculator is set up to radians, because if you plug in degrees, right, and then everything else is set up in terms of 2 pi radians, your math is going to come out all weird. All right, so let's start writing out what's going on. So with theta radians, so theta is our angle. So I've got the change in theta as a function of time, right? So my theta is changing, right? Every 8 seconds, I go through a whole circle, right? That's my 2 pi. So that I would say I go through 2 pi, that's my delta theta, and I go through my change in time is 8 seconds, right? So we're looking at, this is pi over 4 radians per second. Okay, so that gives us my d theta dt. That's going to help me when I do a chain rule. Okay, so let's see, let's think about it. So I've got an angle. I've got this distance for sure. This is 0.25. I've got x. Okay, so if I think about, and this is a right angle because it's straight out, so it's a right angle. So I can think of my right angle tricks, my sine and my cosine and my tangent. Well, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. That all relies on a hypotenuse, but my tangent is opposite over adjacent. So I'm going to think about my tangent of theta opposite over adjacent. I want the tangent because it's dealing with x and my given, right? I don't have to try to figure out my hypotenuse as a function of x. All right, so now opposite, that's going to be x over 0.25. So I can solve this for x, right? So that means I'm going to get x equals 0.25 tangent of theta. I had to come up with that equation myself. Remember, our goal is to solve for dx dt. That's the speed, right? The speed of the beam of light and the speed of the child. So now I have an x equals tangent of theta. Okay, this is in terms of theta. We're going to work with that in a minute. So let's do this. So when I do this, I'm going to say dx dt. Okay, which means I'm going to go 0.25 d dt tangent of theta times d theta dt. This gives me my chain rule, which allows me to go from things in terms of theta to things in terms of x, okay, in terms of t. All right, so let's plug in what we know. So 0.25 tangent of theta times, oops, I should have taken the derivative of my tangent. Sorry, let me fix that. My derivative of my tangent, right, is secant squared of theta. Now d theta dt, we were told d theta dt was pi over 4. Okay, so still, this is in terms of theta. Now I have to go back to how I related x and theta together so I can solve actually for theta. So, and I want to do this when x is equal to 0.5. But I have to convert this, so I'm dealing with x instead of theta. So must think about theta in terms of x. Okay, so I'm going to go back to here. So I'm going to say x over 0.25 equals my tangent of theta. Okay, which means x over, so this when x is equal to 0.5, because that was what we were told at the beginning, when the beam is like half a mile out. The beam is half a mile out. How fast is that child running to keep up with that beam of light? So when x equals 0.5, I'm going to get 0.5 over 0.25 equals tangent of theta, which is 2 equals tangent of theta. So I can go inverse tangent 2 equals theta. So this is my theta. My angle in radians is what I get, 1.107 radians. Okay, so right, the beam comes straight out, the lighthouse is straight out. When we're at a half mile, that angle is 1.1, roughly 1.11 radians. Okay, so now I can plug that back into here, right? Because I figured out my equation. So x t when x is equal to 0.5 is going to equal to 0.25 secant squared of 1.107. Okay, make sure your calculator's in radians, otherwise they'll get all messed up, times pi over 4. Okay, and then what I got was approximately 0.9817, which is miles per second. That's really fast, right? The kid's running 1 mile per second. That's faster than I can run. Mile per second, right? How did I do that? Let me just write that down in a different color. How did I get this? Okay, this secant squared. So secant on my calculator, I did this. I went 1 over the cosine of 1.107 in radians. And then I squared it. And then I multiplied it by 0.25. And then I multiplied it by pi. And then I multiplied it by 1 over 4.5 again. Okay, that's how I got this. So I don't have a secant squared button or a secant button on my calculator, but I have a cosine. So I found the cosine, took the reciprocal, squared it. That gave me my secant squared. Okay, and that's how I got 0.918 miles per second. Okay. Right. Guess I'll see how we did that. Everybody loves word problems. So that's it for chapter 2.8. It's just your basic, your other trig functions that are based on sine and cosine. Okay. Does anybody have a quick question on homework 2.6, 2.7, 2.8? My 8 o'clock class asked about 2.7 question 33. I'm going to post that. I'll post that to our class too. So if you were thinking of asking that one, just hold your question on that because I'll post it later today. Post a solution for that. You guys can put it in the chat if you want. Or if nobody has questions, then we'll just call it a day. Let's see. I said, but is lesson 2.0 on the exam? Yes, lesson 2.8 is on the exam. The syllabus from the department suggested we include 2.9 and Appendix A on our exam. We spent a lot of time on earlier chapters, chapter 1.3, we spent a lot of time in that. So we're technically a little bit behind on our lectures, right, where we're supposed to be in terms of chapter sections because we went a little slower than what was suggested by the department. So we're going to have 2.8 on the exam. 2.9 and Appendix A will be next week. Okay. So yes, 2.8. 2.6 question 37 is a question. Let me see. Oh, 37 is also a really long one too. That took me about a whole page. I'll post that too. So chapter 2.6 question 37. I'll post that one later today. This is my solution took, you know, about a page to do, so I'll post that later. Anybody else have a really short question on the homework you want to ask? Okay, great. So take a look on our modules page. I'll post these two solutions, 2.7, 2.6. And if you have questions on other homework parts, you can come to office hours today or on Wednesday. Don't forget, Wednesday is a review class. I am not going to be presenting anything. I'm not going to be, you know, talking about anything new. So it's going to be up to you to come prepared to ask questions. You can ask questions on homework questions. You can ask them on the review problems. And this goes all the way back to the beginning of the semester. Okay, so I posted a whole bunch of old exams so you can see the kinds of questions that we were asking about. Anyway, if nobody has any questions, we'll call it a day, and then make sure you come on Wednesday with questions, okay, so that you guys are going to be directing the class on Wednesday. Okay, have a great day, guys.
Thank you.
Take it easy.
Thank you.
Bye-bye.
Thank you.